Welcome back. We are now going to start talking about a surprising connection between vanishing points and vanishing lines and reflective surfaces or reflections. And what's really interesting here is you would think just on the offset there'd be no connection between reflections on a mirrored surface or a beautiful lake and the vanishing points from parallel structures in the world. And now we're going to see the really nice connection between this. So let's first just start with the basic geometry of a reflection. So I'm showing you here a camera. I'm showing you an object, a pawn out in the physical world. This orange thing is the mirror, and what you are seeing in gray, equidistant on the other side of the mirror, is the pawn's reflection. Geometry is super straightforward. So camera, there's a ray that goes from the pawn to the mirror. Splice out perpendicular equal angles here, angle goes up to the camera, and then if you extend that line all the way out, you will find where the pawn is going to be shown in the reflection. And just from this very simple geometry, you don't even have to derive it, we get the equidistance here. Now it's going to turn out the equidistance is not what's interesting here, but this is, we know that this is the basic geometry of reflections. We see things in an equal distance inside the mirror relative to my distance to the mirror. Now what's interesting here, let's take a top view of this scene that I just showed you here. So again, world here, mirror image in gray, orange is the mirrored or reflective surface. Take 2 points now on the pawn, on either side of the top of the pawn, and draw a line, would you, for me, please, that would connect it to its mirror image. Well, those are just straight lines. So if I look in a mirror, and I want to know where my eye is, where my head is, where my hand is, I just draw a straight line, right? Just perpendicular to the mirrored surface and draw it equidistant into the mirror, although it's going to turn out that doesn't matter quite as much, and I figure out where my mirror image is on the other side. All right, so we have in the physical world, and obviously let's be clear, I can't take this image. Everything to the right there is a mirror image. I literally can't see that. It's behind the mirror. But it exists geometrically. And so why is parallel structure interesting? Well, we just finished talking about vanishing points, which are what? Points that converge due to linear perspective projection. Parallel structures converge to a point. Okay, so we know that there's something special about parallel structures. All right, let's go back to our scene here. You can see this is the same scene as before. I've got that checkered floor. I've got the boxes, and now look what I've done. I've thrown a mirror into there that you can see right there. So you see the mirror image of the floor and the 3 crates. Here below is a schematic of that scene right there. So what are you seeing? Again, on the left are the 3 crates. In the middle there is the mirrored surface in orange, and on the other side is the mirror image, drawn exactly the way I promised. Parallel structures, equidistant. So each box is equidistant to the box on the other side. Again, everything to the right there is virtual. I can't physically see that, but, well, I can see it in the mirrored image, but I can't see it from this top view right here. Now, why is this interesting? So let's look at those lines that I've drawn here. What have I done? I've connected a point on an object to its corresponding point in the reflection. And I've said that those are all going to be, in the physical 3D world, parallel to each other. Yeah? Different planes, but all parallel to each other. Well, what do we know about parallel lines on parallel planes? They intersect. And so, in fact, if I take a bunch of points on it, you can do this, by the way, at home. Go stand in front of the mirror, go to an angle, take a picture of something, and do what I'm about to do here. Take a point on an object, draw a line to the corresponding point in the mirror image. Be really careful, by the way. It's really hard sometimes to see which point corresponds to what because everything is mirrored imaged. And then just draw all of those lines, and you get something that looks an awful lot like a vanishing point right there. Yeah? So that is simply the result of the fact that when we were taking the top view of that mirror, objects over here, reflection over here, and mirror here, those are parallel. Now what I've done, I'm taking a picture at an angle. So this is projective geometry, plain and simple. Same as the vanishing lines I computed from that checkered floor. It's the same as if I was looking at that floor top to bottom, all of those lines on the floor would be parallel, but when I look at an angle, they converge to a vanishing point. Same thing is going on here, it's just that the lines now here are well, sort of virtual, if you will. They're not actual lines, but they are connecting points on an object to points on the reflection, and all of those converge to a single point, and it is effectively a vanishing point. Now, we also talked about the orthocenter, or the principal point. So let me remind you what that is. Take three mutually orthogonal surfaces and compute their vanishing points. All right, so first of all, I can see three mutually orthogonal surfaces on a crate. Yeah, 1, 2, 3. Sure. What's happening here with the mirror? Where am I getting 3? The mirror is flat. Well, let's see what I've done here. So I've taken the top 2 lines of the mirror, that's this one right here. I've taken the sides of the mirror, that's the point at the very bottom right there. So let's agree that those are mutually orthogonal. It's a mirrored surface, it's a rectangle, I'm telling you it's a rectangle. So that makes sense. So now I've got this line, at this point rather, and the one all the way in the bottom there, come from 2 mutually perpendicular surfaces, top and sides of the mirror. Vanishing point, vanishing point. What's that third one? It's the one that goes in and out of the mirrored surface. It is that vanishing point that I just showed you. Why is that mutually orthogonal? Because it's perpendicular to the mirrored surface. Yeah, because those lines essentially were going through the mirror perpendicular to it. And so if I have a rectilinear mirror, I can compute, we agree, 2 vanishing points from 2 mutually orthogonal surfaces. And if I can just see 2 things and get that virtual point right there, I've got my virtual third perpendicular or orthogonal rather surface, and now I can compute the orthocenter, and now you can see that that principal point is directly in the middle of the image in the same way, exact same way as I did from 3 mutually perpendicular surfaces in the physical world using vanishing points. So really similar geometry, and obviously all the mathematics, everything that we did in the previous segment works here. We're just intersecting lines, 2, 3, 4, 5 lines, don't care. All right, let me show you another example of how you could use this. 2 people standing in front of it doesn't have to be a mirror, this is a glass surface, yeah, and you see a reflection in any reflective surface. And as long as you can reliably connect corresponding points on features in the world and features in the reflection, you can start to reason about the reflective geometry. So here I've taken 2 points on the red man, 2 points on the blue man, and they each, of course, converge to a point because it's just 2 lines, but it's not the same point. I've got a problem with my projective geometry. That reflection is wrong for one of these 2 guys. Now, which one is wrong? Well, I can't say just from this image, right? Just from this, I have no way of knowing. All I can tell you is something is wrong with this. But almost always, there are other structures that you can see in the reflection. In this case, there's a little brick a ledge there, and you can see these little lines that are in the world and then reflected on the other side. And what I've drawn here are connecting points from the brick to its reflection. And now you can see that blue man seems to be attached to that window front here, but red man seems to have been put in the wrong place. And what we're going to see in a couple of segments is that when you try to create, you being the human visual system, when you try to put a reflection in a reflective surface after inserting an object into an image, you have no idea where to put that reflection. People put it in absolutely the craziest places. And that works really well for us. Of course, if somebody can do this analysis, well, then they're going to get it right. But let's face it, most people are not going to do that. So we can leverage the fact that people don't have a good intuition for reflections. Again, this is what I was saying in the last segment, is that our ability to reason about 3D projective geometry and 3D physics and geometry of the world, it turns out is not very good. In fact, it's surprisingly bad. And we're going to see that over and over again as we go from vanishing points to reflections to lighting and to shadows, that our visual system often fails us. That's important for us as analysts to understand when we're analyzing images, and not just trust what we see, but also learn how to exploit what the forger is going to, what types of mistakes the forger will make. All right, so now we've done vanishing points, vanishing lines, we've done reflections, and what's next are shadows. And again, you're going to see this really beautiful connection between all 3 of these. They are going to share the same basic analysis technique, which is intersecting lines, looking for convergence. And the shadows are going to be a little bit more involved, but we're going to see that we're going to carry that same underlying technique to shadows. All right, so I'm going to stop here, and when we pick it up, we'll start talking about lighting and shadows. See you in a little bit.